And we are live. Welcome back to Math with Doug. It is percent with Doug because we're in a percent unit. The dog is uncomfortable, that's why she's squirming. Okay, I have a better grip on her now. The dog is not going to be involved. Her job is to sit there and pay attention and not interrupt. So I'm going to let her get comfortable to do that right now. Down you go. Okay, lie down. Stay. Thank you. Okay. So what else is going on? It's cold outside. I don't even want to talk about it. I'm tired of the weather. And I'm wearing West Bromwich Albion, which is a team from the English soccer, which is sometimes in the Premier League, but not always. Nice logo. It's got a bird on it. It's cute. And I like this little baby blue accent. It sets off my eyes. And of course, my eyes might get close to the camera sometimes. See, they are blue. In this lesson, because I want to let students interact a lot with this lesson, because it involves estimating things, which means we could call it a guessing game if we wish, but it's not really that much of a. I have my opinions over whether we're really guessing or we're doing something else that's a little bit more interesting than guessing. We'll see. We'll get into the examples, but to calculate percent error is what we are doing. Percent error is not very different from percent change, which we did a lot of examples of last week, but there are some slight differences. With percent change, when we end up with a negative value, it matters because we want to be able to say whether we have a percent decrease or a percent increase at the end when we give the percentage of our answer. But percent error, we're really focused on how far off are we from the official value or the correct value. It depends. Sometimes you would get the exact value by looking it up in a book. Sometimes the approximate is something you get as a result when you do an experiment, but sometimes it's a guess. So we have approximate minus exact over exact, very similar structure to last week's formula. But when we get a negative number in the numerator, we pretty much ignore it. And otherwise, the math side of it is fairly easy, but it's a really useful concept for science. So the reason to teach this in math class is because students are going to use it in science class. But right now we're going to focus on playing some games where we guess or make educated guesses about values and compare them to the real values. I have a whole bunch of real values written on my chalkboard wall right over there where you cannot see them. And those real values have to do with things like this colorful glass full of colorful things. And so we may as well just get into it. Okay, so we'll start with this. Let's start with this. Is that what I started? Yes, it is. That's what I started with my examples. So I'm going to do quite a lot of examples. We have 5 different colors of things in here. And I know how many of each there are. Now, I will admit what these are. These are Cuisenaire rods. They're very useful for teaching all sorts of things in math. And I'm using them now because there's a lot of them and they're fairly small and they fit into a glass so the students can see them. And they come in different colors. So it means that we can have a whole lot of games where we try to figure out how many of something is in there. So let's just get started. I think the best way to understand this is to start it. I know the exact number of little beige cubes that are in here. If I hold this steady enough, you will see some of the pieces are beige cubes. But of course, the students can only estimate that because you can't see the whole glass really well. You can't dump it out and count them because if you could count them, well, you would get the number perfectly right on. So I am waiting for students in the chat to tell me how many little beige cubes they think are in here. That's going to be the first time we use the percent error formula. And I'm watching the answers come up and I'm just going to be sometimes randomly choosing them. Sometimes with some of today's examples, I'll be trying to find the student who gets the closest. But for here, we just want to know, how many do you think are in here? And I'm going to get ready to do the formula. So this is exactly what I meant to show this to the camera. This is exactly what I'm talking about. This is not one of the ones that was in here. This is a different one that I'm keeping separate. And it is a little beige cube. Put that down, put the glass down. And now I'm going to look at some student guesses. And is it a guess? That's what I was talking about before. Are we really guessing? We'll keep on. We will discuss this. Okay, approximate is going to be the student's guess. And I see a student has guessed 31. So 31 is our approximate. Exact is how many beige cubes are actually in that glass, and I know how many there are because I counted them when I put them in there. And I can tell you right now, I'm referring to my list of values, the exact amount that are in there is 27. So very easy, fast formula to fill in. 31 minus 27. And then we have to put a 27 down here. Why? Why do we put the 27 down here and not 31? Because the numerator is showing us how far off the guess was. And the denominator is showing how much there really were. We want to see how far away the guess was from the right amount, and doing this will allow us to calculate that in the form of a percentage. So of course I have to write times 100. Okay, 31 minus 27 of course is 4. We have 4 over 27 times 100. Is this all going to fit nicely in the rectangle of the Zoom? Yes, it is. Okay, chalk dust all over my calculator. Okay, 4 divided by 27. And thank you, student, for your estimate. And I get 0.148148,148. So that's giving me 0.148, which repeats, but I think 148 is enough. I've gone to enough decimal places, times 100. And of course, multiplying by 100 is very easy with decimals. We're jumping the decimal 2 places to the right. So our answer is 14.8%. The percent error is 14.8. And this time, when we did the subtraction, we got a positive value in the numerator here, because that happened because the student's guess was larger than the correct amount. So we didn't have a negative sign we had to ignore. We got a positive sign. When there's a negative sign, we will ignore it. Okay, so the percent error this time was 14.8%. That shows how far off that guess was from the actual. And I think it's a pretty good guess. Now I'll talk about that guess thing. Is it really a guess? Kind of yes, kind of no. Because the student doesn't have nothing to work with. They're not just guessing any random number. They can see pretty much how many items in total might be in this glass. They can see that the little beige cubes are actually the smallest of the items that are in the glass. And that helps us to make what I would call an educated guess. So the approximate isn't a pure guess, it's an educated guess. And we're not too surprised that a student managed to get this close to the actual value. So let's do it again. This was fun, let's do it again. Anything that involves the students being able to guess, when they're not really guessing, they're actually estimating in a very intelligent way, is always fun for the teacher and for the students. Let's do it again. I have 5 different colors of shapes in here, and we can do it for all 5 of them. So we will get plenty of repetition of using this formula. Good start. Let me get my eraser cloth. I will erase, I'm keeping the formula there for the whole lesson, but I'll erase all of the answer we got for the beige cubes. Next one I have, now I didn't necessarily start from the smallest and go straight through to the largest. The next one I'm going to do is the green. Now, the green Cuisenaire rods are longer than the beige. And you could actually count quite a few of them if I were to twirl this around slowly enough. There might be a bit of confusion over, wait, is that one green or is it yellow? Because the green and yellow, the shades are not really that different, especially held into a video and held with shaky hands holding it in front of the camera. And of course, there can be some green ones right in the middle that we really can't see. So it is a guess, but it's an educated guess. How many green ones do you think is in there? And I'm watching the guesses come in because I want to lean forward at the right moment and choose one. And I can see what my actual is. I don't want to tell you the actual beforehand. That would make the game a little too easy. So what I am seeing is someone has guessed 21. So the approximate this time is 21. And from that, I will subtract the actual number of green. And again, the second time in a row, I forgot to hold this up. Yeah, this is the one I'm talking about. A little green Cuisenaire rod. Great little toys for math. And for building little log cabins and houses and things like that too. I admit I do that. Okay, the actual amount is 23. So this time, the guess is smaller. We are going to get a negative number and then ignore it. And since the exact goes in two places in the formula, I need to write another 23 here, times 100. 21 minus 23 is negative 2 over 23 times 100. And I guess it's a matter of opinion. Should I not show the negative sign now and just ignore it right away? Or should I show it but then start ignoring it soon after? I don't know. I think that's a matter of opinion. I'm going to ignore it once I get to the next step. So negative 2 divided by 23. And of course, you can put the negative sign into this division or not. And it just doesn't matter with this formula. I can just go 2 divided by 23. And I know that I would have had a negative answer. I have 0.08695. I'm going to call that 0.087. So ignoring the negative sign, I just have 0.087 times 100. And I can give my final answer. Moving the decimal 2 places to the right, I have an 8.7% error. And it's as easy as that. It is easy. And it is fun. So let's do it a bunch more times. We'll see how many examples we can fit into this lesson. And we'll see if I made up enough examples or if I'm going to be embarrassed and realize that the lesson is over. I've used all my examples, but I still have more time. We'll see. I have 5, 11, I have at least 13 examples to work with. And I have some ideas about how we can, as a group, improvise some other stuff. But first, I'm going to take a sip of my fizzy water. Calamansi, citrus, and strawberry. Okay, we may as well do all of the colors of these in a row instead of switching to something else and then switching back to these. So we have 3 other colors to work with. This time I'll remember to show. Okay, this is actually a little bit longer than the green Cuisenaire rod. This is the purple Cuisenaire rod, and you can see there are some of those in there. Twirling it around, trying to give people a fair chance to make a good estimate. Twirling and holding in front of a camera at the same time is challenging. But I think you've seen enough so that you can make an estimate. I'm going to erase our green answer, and now we will do the purple one. And I'm giving the students time to type into the chat their guesses. So I'll get started with this. That's the purple. They're also pink, so I have to be careful not to choose the wrong number. Okay, so I see a guess of 14. And I know the exact because I have it written down over there, and the exact is 11. So we have 14 minus 11 over 11. 14 minus 11, of course, gives the positive answer, which is 3. We have 3 over 11 times 100. This is starting to go very quickly, isn't it? 3 divided by 11. 0.2727272727. I could go on forever. 0.273. 0.273. I just choose to round to the nearest thousandth in the decimal. And that means that after we multiply by 100, our answer will be rounded to the nearest tenth. So the percent error is 27.3%. Why is it so big this time? That's an interesting thing to think about. We are asking those what-if questions. What if this, what if that? Although this is more the answer, and we're saying, well, what type of what-if question would have given us an answer like this? Why is it so big? Why is it so big? Partly because the actual number was actually smaller. We had 27 beige, and we only have 11 of the purple. And of course, one of the reasons that happened is because the purple ones are bigger than the beige, and there's only so many I can fit into that glass. But does that mean that as the little Cuisenaire rods get bigger, I always have a smaller amount in the glass? No, it doesn't mean that. I didn't let that happen when I was choosing how many to put in the first place. So, because the difference of 3 is actually rather large when you compare it to the exact, which is only 11. This is why we ended up with a larger percentage. The guess was still pretty good, I think. Okay, so next one, let's do, we did beige, green, and purple. Let's do the yellow ones. The yellow ones are actually the longest of the Cuisenaire rods I have in that glass. So does that mean that the number in the glass has to be really small because they're longer? Well, we don't know. So let's find out by doing the experiment. You can see the yellow. Hopefully you're not mixing up the yellow ones with the green ones since the shades are similar. The yellow ones are actually the longest ones that I have in this glass. I have a matter of opinion. I was calling this pink, the last one I'm going to do, but when I look at it now, it looks red. How could something look pink to me when I was preparing this lesson a couple of hours ago and look red to me now? I don't know. Maybe it's the afternoon light or something like that. There you go. There's your chance to look at all of the yellow and try and figure out how many yellow ones are in the glass. And now we will, while I watch the results come in, we will get ready yellow. 8. One of the students has guessed 8. That is the approximate. The exact turns out to be 9. 9. And therefore I put the exact in 2 places. The 9 goes in 2 places. 8 minus 9, which gives -1. But, of course, this is the point at which I'm going to choose to ignore the negative sign from now on. 1/9. Is that 0.11111? Have I memorized that? 1 divided by 9. Yes, I have. It's 0.1111111. So I'm going to do 0.111, not bothering to put a negative sign, multiply by 100, and that means we have an 11.1% error. Pretty good, pretty good. I haven't been writing down the results after we calculate them, but that might be the closest we've gotten so far. I can't remember now. Okay, anyway, 11.1% error isn't too bad. So the student did a good job in making the guess about the yellow Cuisenaire rods. Now we're going to do the pink/red Cuisenaire rods. It is a matter of opinion whether these ones are pink or red. And I'll show it again. This one. Is that red? When I hold it up to the little timer on my camera, which is red, it looks red. And the little stop button for the recording, the little stop the recording button is red. I'm going to call that red. Okay. Even though on my wall chart over there, I referred to it as pink. So, let's look at the glass and give the students time, take a look. You can see some red ones in there. Some parts of the glass you see quite a lot of red ones, and then other parts of the glass it's hard to find a red one. Well, that sort of happens when things have been put in the glass and shaken up randomly. Okay, so I think I have given the students enough time to come up with a good guess. Let the guesses come in. The red, we are doing something minus something over times 100. Just filling in the skeleton of my formula to give more students time to type in guesses. And I know the right answer, and I see 18. 18 is the approximate, and the real value is 15. Oh, this is going to be a fun one. 18 minus 15 is 3. We have a positive value this time. And 3 over 15 is one that I can convert into a percentage and into a decimal in my head. 3/15 reduces to 1/5, doesn't it? And 1/5 is 20%. This is fun. So 3 over 15 times 100 is equal to 0.02 times 100. And there's no use for me to go to a third place to the thousandth, because after the 0.02 in the calculator there'd be nothing. It would just say 0.02, wouldn't it? Well, I guess I better prove it. In my extremely chalk dusty calculator, which I doubt if people can see very well, 3 divided by 15. Oh, I had it wrong. It's not 0.02. 0.02 is 2%. I'm glad I got the calculator. That would have been embarrassing. Well, it's kind of embarrassing anyway. Okay, it's 0.2. 0.2. Of course, the students all realize that, and if I look at the chat, I'm going to see that a bunch of students are saying, no, Doug, it's not 0.02, Doug, and I wasn't noticing. That sort of thing happens as well. Students are trying to be helpful, and the teacher isn't noticing. So yes, 0.2 times 100, which is 20%. This guess represents a 20% error. we don't have to say positive or negative because it's not about increase and decrease this week. It's just about error. It's just about how far off were we. Okay, that game was fun. We have gotten exactly to the 1/3 mark of the time of the lesson that I had planned, although the lessons are allowed to be slightly longer or slightly shorter. But we're at 1/3 mark, and I have gone through my first game, and I have 3 games planned. So my estimate, my approximate, my guess as to how long it would take to do all these examples, maybe I can calculate the percent error of my prediction of how long this lesson will take. We could do that. But not yet. We have to find out how long it took first. We have to get to the end of the lesson. So I'm going to erase. I'm going to put this jar of Cuisenaire rods aside because I think we're probably finished with it. Not putting it too far. I'll put it somewhere over here where I can still reach it in case I decide to bring it back into the lesson towards the end. I'm going to take another quick sip of the fizzy water and notice whether someone seems to be asleep. And she does. Okay, needed that. Next game. Not very different. A bigger jar, and it's a jar, not a glass this time, a bigger jar, and it's also colored shapes that are good for teaching math, but these are little geometric shapes. Love them. Fun to play with, but fun to learn math with as well. So we have 6 colors of these. We have yellow, hexagon, well I may as well show them, so I have them here. I'm going to show all of the shapes in advance so that I don't forget. We have yellow hexagons. We have red trapezoids, called trapeziums in some places. We have orange squares. And we have green triangles, little itty bitty green triangles. And for some reason, there's 2 different rhombuses. We have the sort of whitish, beigeish, I'll call them white rhombuses. And we have these other blue rhombuses. Why? Why do they have 2 types of rhombus? They don't have 2 types of trapezoid. And there are more than 1 types of trapezoid in this world. So I don't know what the logic went in, but they are fun to play with. Okay. So I have them there in case I need to remind you what we're looking for. And we have a jar with a whole bunch of them. And I have recorded how many of each I put in there, and I tried not to make it too obvious because we can see that the yellow ones are the biggest and the green ones are the smallest, so I don't want it to be too obvious. And with that knowledge, the student is better able to make an educated guess. It's not a pure guess. So the students will guess the amounts of things, and that'll be the approximate, and I know the correct amounts that I actually put in, and that is going to be the exact. So we know what to do. Let's play the game. Which shape should I do first? I'm going to do green triangles first. Okay, so the green triangles look like this. That one doesn't count. And you can see the odd flash of green in there, but there's more. This jar is bigger, and there are more shapes altogether in there. And there are plenty that could be hidden in the center where we really can't see them. So it's a bit more of a guess. Okay, and the guesses are coming in. I'm watching the chat and keeping an eye on that. Okay, the guesses are coming in. So I'll get the skeleton of my formula ready. And then I'll look at the guesses that come in the chat, and I'll quickly choose one. But while I'm doing that, I'm checking green triangles. There they are. Okay. 9. I see 9 as a guess. And I don't blame a student for guessing 9. When I look at that, there just don't seem to be that many green triangles in there. Or at least there just doesn't seem to be very much green when you look at all the colors. So 9. The actual number of green triangles, though, is 16. So here's one of the times where we get the negative answer when we do the subtraction. I have to put 16 here as well. Don't forget that. Okay, 9 minus 16 is negative 7, but I'm just going to write 7. And we have 7 divided by 16, and I've learned my lesson. I'm going to use the calculator every time. 7, oh, show the times 100, please, Doug. 7 divided by 16 0.4375. It only goes to that many digits, so I'm going to write it all. 0.4375 times 100, which means we have a 43.75% error. Now, I hope the student who guessed the 9 doesn't feel bad. But I don't think that the student should, because I see all the guesses. And some of them it's more difficult than others to make a guess come close to the real. And that green triangle, I think it's a bit of a challenging one. So we have our answer, 43.75% error. Let's do another one. Right away, let's switch from the smallest to the largest. The largest are the yellow hexagons. And you see quite a bit of yellow when you look here. The yellow ones, they want to nest together, I'll tell you that much. I really had to shake this quite well to make sure they didn't all stack up together into one big yellow blob. That would have made it a little too easy. So there you go. I'm giving you time to look, and the guesses are starting to come in, so I'm going to put the jar down. These are glass jars, and all the things I'm using are made out of glass. Maybe that's a mistake. I should get myself some good see-through plastic containers for this. Okay, so I'm looking at the guesses, and yellow hexagons. 18 is the guess that I am using, and yellow hexagon, the real amount is 21. We're getting a negative number again. Remembering where to put the exact goes in 2 places. The one on the right is the one that's in 2 places. That's another way to help you remember it. If we were to do exact minus approximate, it would still work, but we don't want to do that. We don't want to keep on changing how we put things into the formula, because that's asking for mistakes. Because that would make us end up making a mistake with what we put down here. I think that's what would happen. 18 minus 21 is negative 3. I'm going to call that 3. 3 over 21, oh, that reduces to 1/7, but I don't think I have memorized the decimal that goes with 1/7, and I'm not going to try to do it in my head anyway. Okay, 3 over 21 times 100. So what is 1/7 in decimal form after all? 3 divided by, I'm going to guess it's 0.14 something. Divided by 21 equals 0.1428. It's not, again, I said I'm going to guess, but was that really a guess? I do this a lot. So I have a feeling for certain decimals that you see more often than others, more than a lot of people, because I do a lot of this sort of thing. So it's not really that much of a guess. It was a memory, a not so clear memory. 0.1428, I'm going to put 0.143. I'm liking rounding to the nearest thousandth in this type of formula. Times 100, which means this student's guess was a 14.3% error. Okay, pretty good guess. Let's do another one. Another shape, another color. Erase. Okay, what's another one? Let's take the blue. We have a blue rhombus. Lovely little thing. And there are definitely some blue ones in there if we take a look. So what could we do when we're trying to come up with a strategy for guessing to try to come up with a good guess, an educated guess? One thing a student might do is try counting them, all the ones that they can see, and then say, okay, it has to be at least that many, and I'm going to add a few. I think some of the students would be using a strategy like that. But of course, it's hard to count things when you have a teacher holding them in his wobbly hands and spinning them at random speeds and talking the whole time and forgetting to hold it in front of the camera very well, that sort of thing. But if I were doing that, I'm going to try to do it. So I don't remember what the actual amount, I'm going to try. And we'll do this twice. We'll do it my guess and a student's guess. I have to not peek over at the answers. I promise you, I'm trying to get the chalk without getting too close to those answers, and I'm standing with my back to them. I can't remember how many blue rhombuses there were, but using that strategy, and of course having an advantage over the students, because I can hold it still and take my time counting the blue ones in a way that the students have no control over. I'm saying, I'll say 1, 2, 3, 5, 6, 7, 13. I'm seeing about 13, and I'm guessing it's going to be in the middle of all those where I can't see them. I'm going to say 20. I'm going to guess 20. So that's me. But I'm also taking one of the guesses that were typed in. And I see a guess of 24. So I'm going to do this twice. Okay, still not looking at my actual correct value. So teacher, and then over here we have student. 20 was my guess, minus the exact, and I haven't gone over and looked at the exact yet, but I'll finish this. 24 minus the exact over the exact times 100. And what was the exact blue rhombus? 17. 17 was the exact. So I apologize for getting closer than the student, but I do admit I had that advantage of being able to actually hold that thing right in front of me. And some people might say, you probably remembered how many you wrote on the wall a couple hours ago. Well, I didn't, but it's a valid accusation. It could have happened. Maybe my memory would be that good. 20 minus 17 is 3. 3 over 17 times 100. 24 minus 17 is 7. 7 over 17 times 100. Neither of these is giving us a negative value because both of us guessed more blue rhombuses than actually were there. Let's get the percentages. 3 divided by 17 is 0.176 blah blah blah. It's, well, 0.1764. I should at least say the fourth digit after the decimal because then you know whether I'm rounding correctly. 0.1764 rounds to 0.176. So therefore the teacher had a 17.6% error and the student, 7 divided by 17, 0.4117, so 0.412, 0.412, which is a 41.2% margin of error. That's quite a big difference in the in the percent error. That's quite a big difference. Not a margin of error, that's something else. Shouldn't have said that. But why? Again, because the numbers are kind of small. So being off by a couple makes a bigger difference than if the actual number is really large and you were off by a couple. So that explains why this is so different. That was worth doing. That was a good what if question. What if the teacher had an unfair advantage and wanted to compete against the students in the game? That's what would happen. Teacher beats the student, and we're all kind of going to have our opinions as to why. It reminds me of the time I was teaching phys ed, and I was a substitute teacher, and it was in a school that in the gymnasium, in their storage room, I looked at all their stuff, and they had an earth ball. An earth ball, a ball, and I don't know, the diameter of the ball was at least 8 feet. It was huge, and we played earth ball, and we had a game that involved who can get the ball from one end of from the middle of the gymnasium, which team can make the ball touch the other team's wall. Very simple little earth ball game, and we had one round where it was all the students in the whole class against the teacher. So it was just me against all of them. There were around 30 of them. But they were in the 3rd grade, so the tallest ones were around here. And I was able to pick up the earth ball over my head, and I walked all the way, and they couldn't stop me. I walked all the way, and I touched the wall, and I won that game. Unfair advantage on the part of the teacher. Okay, I already erased. I don't need this. I need to do the next color. We're nearly finished with these. We have done yellow, blue, green. Is that all? Yellow, blue, and green? We haven't used the white rhombuses yet, or the red trapezoids, or the orange squares. We didn't use the orange squares, did we? No. Let's do the orange squares next. Here's an orange square. And it looks to me like there are a lot, or is that an illusion? The light is in your advantage right now because the light's shining on this jar. For me, I have the light on the other side of the jar, so it's kind of hard to look at. I'm making excuses, but I'm not competing against the students this time. One of the students, I'm going to choose their value. How many orange squares do you see? And I am going to take that value once I get the skeleton of my formula ready. Okay, and let me see what the real value is. One of the students chose 30. 30, what seems high. That seems high to me, but I already looked at the real value, so it's not high. It's actually really close because the real value is 31. This is going to be a nice small percent error. Very good job on that student. How did the student do that though? I kind of wonder, because when I look at this, it really doesn't seem like there would be that many orange ones. Maybe now I'm seeing that they kind of stacked up down here. There's a lot of orange ones lying flat. I can see about 8 of them in this one little region. Now I'm starting to understand, but I know the student couldn't have seen that very well. It's hard for me to see. Okay, so 30 minus 31 times 100, that's negative answer. We're going to have -1, but I'm just going to write 1 over 31 times 100. Good result. I wonder if any of these examples are going to have the student get it right on, which would be a 0% error. That would be cool, but I'm not going to force it to happen. If it happens, it happens. Okay, I need my calculator. That's why I walked over there. 1 over 31 times 100. 1 divided by 31. 0.0322, so 0.032. 0.032 times 100 is only a 3.2% error. Smallest one we've had in this lesson, I'm certain of that now. Very, very good guess. Okay, 2 more shapes. Let's do them both. Let's get that done. How are we doing for time? We're getting, this game is taking about as much time as the first game. The third game is a little different, and there's going to be some extra steps in it. I'm kind of improvising this, so. But I have some data to work with that are written over there, and I'm really not sure how long this third game is going to take, so we might have to improvise something at the end. Let's get rid of this extremely good guess. And the only 2 shapes that are left are or is there only one shape left? The white, yeah, the 2 shapes, the white rhombuses and the red trapezoids. Let's do the red trapezoids. You can see the red jumps out at you. It's hard to get it mixed up with the orange. There's some orange and some red close together, but I find if looking at it live like I can, it's really easy to tell the difference between the red and the orange, and I'm giving you plenty of time. And now I'm going to choose one of the students' guesses without looking at the real amount that's written over there, because I don't want to influence my choice of which student's guess to put. So I'm going to say, look at these guesses. 18. I'm going to take 18 as the guess that I will use. Now, of course, lots of guesses are coming in, and some of the students are getting closer than the ones who I choose, but the guesses in the chat go zooming by so fast. Sometimes the best I can do, I don't want to have to go and try scrolling through the chat to look at all of the answers. So 18 minus, and the real value for red trapezoids, 14. 14. There are only 14. I thought it was more than 14. Okay, when I was just looking at it just now. So the exact, of course, goes in 2 places. The 14 goes in 2 places. Times 100. 18 minus 14 is 4, not a negative value. Doesn't matter anyway. 4 over 14 times 100. And 4 divided by 14. 0.2857, so that's 0.286. Times 100, which is a 28.6% error. And we only have 1 color left, which is the white rhombuses. I'm starting to get mixed up. So if I accidentally did the same color and shape twice, would that be a problem? I'm realizing no, not really, because we could play the same game twice. And of course I choose a different guess, and so it's valid. Okay, so the white rhombuses are these ones that aren't really white, and they're very skinny. And, I don't know if they're that easy to see though when you look at the jumble of colors and shapes. So, I'm not even holding this in a very good place. So, there we go. Slow down a little bit there, Mr. Doug. And that's enough time. And I'll look at them myself. Okay, I see a guess of 24, and that's the one I'm going to use. Oh, I have to erase. 24, 24, 24. I'm not looking at the real yet. 24 is the approximate. It is the student's guess, 24. And the real for the white rhombus is 19. Okay. 24 minus 19 over 19. Exact happens twice. 24 minus 19 is 5. We have 5 over 19 times 100. And then using calculator, not trying to be clever and do it in his head. 5 divided by 19. 0.2631, so I'm just going to write 0.263 times 100, which is a 26.3% error. Okay. We've done all of the shapes in that jar, so now I can take another glass jar and put it way over here out of the way so that I'm not going to accidentally break it. And I can move on to the third one, the glass full of dice. Okay, so this is a slightly different game. We're going to first guess the number of dice, but then the students are going to try to calculate. Oh, we have a couple. I'm just going to guess the dice for now, okay? But there's going to be at least 3 and maybe 4 stages in this little experiment. And I like it. I like that I decided to do something different. Because these guessing games, I don't want the students to find it boring. I could probably go in there in my cabinet and find colored paper clips and put those in a little tiny glass. And we'd just really be doing the same thing, wouldn't we? Let's do something a little bit different. But it starts off very similar because we have these dice, and I will explain why this one is so weirdly colored. It's because when I paint things, I'll put dice on the surface and then put the thing I'm painting on the dice so that I can paint the bottoms and reach more of the shape without getting paint all over the tabletop. So a lot of my dice have paint on them. So this one has some blue paint, and I think, oh, there's some gold paint and some green paint. There. Can you see the gold and the green? There's the green. There's some gold. Okay, so they're normal dice, and they're standard. They're a standard size. And this one is not in the glass, but there are a bunch of them in the glass. That's the only thing that's in there. It's not a bunch of different things like we had in the other jars. Does that change how difficult or easy it is to estimate how many dice there are? Or does it make it easy? I think it might make it easier. So I'm going to let students guess how many. And I see a guess of 27. So I'm going to use that. The guess is 27. And the exact number of dice is 34. 34. Over exact of 34. Again, we're getting a negative answer, which we can ignore the negative sign. 27 minus 34 is going to be negative 7. I'm just writing 7. 7 over 34 times 100. So being off by 7, and analyzing the results again. Being off by 7, we're quite far off. Some of the other guesses were so much closer. But the total number is kind of large compared to some of the others. So my prediction is this is actually going to give a fairly small percent error, and it's going to end up looking like a better guess. So the fact that we actually have exacts that are much larger numbers could result in much better guesses. That's kind of interesting. So I should do an example, and I don't really have anything ready, but I could do an example where I know that the exact value is quite large. I'll try and think of that while I'm going along, because I may need to improvise a couple of extra examples for the end of this lesson. 7 over 34 in the calculator. 7 divided by 34 equals 0.2058, which means 0.206. Not time, not multiple, equals 0.206 times 100. Oh, well, that's a 20.6% margin of error. I keep saying margin up. No, not margin up. That is a 20.6% error. Okay, and it's not too bad, but it's a little higher than I was expecting. So the bigger number, still, we had some in the 40s with some of our guesses. So when you have a small number down here and over here, the chance of this ending up being big, I think, increases. This is what I'm learning from this experience. But I wanted to do a couple of other things with these dice. And I want to start doing some different looking stuff, but we're still going to use the formula. So we are finished with the number of dice. Now, I'm going to be guessing mass. Mass. And I call it mass and not weight because I am going to be taking answers in metric. So in grams, we are going to guess how much, well, what is the mass of one of those dice? I'll write mass. No. Mass of dice. Mass of one dice. And of course, some students might be trying to correct me saying mass of one die, but we're allowed to say mass of one dice or mass of one die. I'm saying mass of one dice. And then mass of the glass. So what we're doing is we're using some values together, both of which were estimated. Instead of just estimating one thing like in all those other examples, we're actually estimating two things, and then we're going to bring it together. So let's find the mass of one dice first. And that's going to come in as guesses in grams. And it's small, so it's not going to be a very large mass. And the glass, I will remind you of what the glass looks like. This is this glass, kind of a tulip-shaped sort of thing. Not especially large. And you can get an idea of its size by comparing it to the size of the dice, which are, I think, very standard, probably the most common size for dice that you would see in North America at least. Okay, so I want guesses as to the mass of a dice and guesses as to the mass of a glass, and we're going to find the percent error for both. So this is going to be a minus sign, the fraction line times 100. And I am waiting for more, I want more guesses to come in. And if you're guessing both, you have to say which is which. So if you're going to type in, you can type dice something grams, glass something grams, if you want to put it all into one chat message. And then this looks the same, subtraction line times 100. Okay, I'm reminding myself. Okay, so 4 grams is the mass of one dice that I am going to select from the many guesses of the many students. And then for the glass, I'm kind of influencing the results by peeking at the answers, and I admit it. 125 grams. And those are both approximate because they were guesses. And then the reals I have written down over there because I weighed them. I determined the mass of them before the class started. And the mass of one of these dice, it turns out, is 2.3 grams. So I have to write that here and here. And the mass of the glass, and that was kind of funny, is exactly 100 grams. So I'm writing that here and here. Lots of hundreds in that one. So let's see. I'm trying to think of what I'm going to do next because the order in which I'm doing these things sort of influences whether the students have, well, what information the students have when I ask the next question. I'm realizing maybe I should have given some of the information in a different order, but it's too late now. So I'm going to do this. 4 minus 2.3, which is going to be 1.7, over 2.3 times 100, and then 125 minus 100, which is going to be 25, over 100 times 100. Both of them happen to be guesses where the guess was bigger than the real. So both of them we had positive numbers in that numerator. This one we can do on our heads, can't we? 25 divided by 100 reduces to 1/4, which is equivalent to 0.25 in decimal. So 0.25 times 100. Need more chalk. Well, that piece of chalk is nearly at its end, which is a 25% error, which is not too bad. And then 1.7 over 2.3, I think I'm going to use the calculator for this one, and I'm watching the time as well. 1.7 divided by 2.3. 0.7391, so I'm putting 0.739. $73.9%, really? Oh yes, yes, because I'm looking at this and I'm not thinking of the original guess. The original guess of 4 actually is quite far from the actual mass of 2.3. So we have a 73.9% error. And that's actually not too bad, because it would be reasonable for someone to guess double the actual weight, or only half the actual weight. If you were to guess double the actual weight, that would be 100% error. If you were to guess triple the actual weight, guessing 6.9 grams, for instance, in this case, then it would be a 300% error. So getting a percent error less than 100, actually, in some circumstances, it's not that bad. Okay, so now this is where I kind of messed it up. I wanted to make the students calculate the total mass of the glass with all the dice in it. Which, of course, they can do too perfectly now, because I gave the exact values. So I'm going to have to improvise something else. What I'll do is I'm going to stop with this. The dice were finished, and we're going to do something else. But this time, instead of the students having to guess, I'm going to let the students get an exact value, and I have to guess. So that might be a little bit more tricky, but I think I can do it. And I have only a few minutes left in this lesson, so I guess I can be forgiven if I have to slow down to carefully try and make something happen. The next time I teach this lesson, I'm going to do this dice thing in a different order so that we can get the students to figure out, it's not really so much a guess at all at that point, figure out what you're going to do with some multiplication and addition, the total mass of the glass with all the dice in it. But to do that, they can't know the exact mass of the dice or the exact mass of the glass, because that makes it too easy. So, I have an idea of how I'm going to do that. Now, what can the teacher guess where I can't know the real, where the students know the real? So the students know some real stuff. For instance, wherever you are in your house, someone who lives in a house with a fairly large family, I try to guess how many people are in your family. So can't type in how many people are in the chat because I'll see it. That's not a guess. So that was one idea. How tall a student is. When it's Zoom, I see people's faces. I don't see how tall people are. So that one, I like that one. Let's do that one. So I'm going to have a student, don't say your height, because then I'll know. So say pick me, or should I say just pick me? Yeah, just say pick me. And I'm going to choose one of the pick me's and actually pick me and say pick me and tell me how many people you have in your house right now. And I'm going to choose an answer that's different from everyone else's. That's what I'm going to do. So that I can choose someone. I don't want to say someone's name while I'm doing the lesson. So I don't want to say the name. I want to be able to identify the person without a name. So I'm going to identify you by telling you who said pick me, who has so many, okay, and I'm seeing the results coming in. Well, there's a fairly large number of people in one house. So, okay, the person who said pick me and has 9 people in their house right now. Okay, it's your height that I'm going to try to estimate. Don't stand up and get further from the camera. I don't want to have all sorts. I'm going to take a look. There you are. Okay, so I can see who it is, and I can see which zoom rectangle to look at. And does it even look like I'm looking at you? Where's the lens on this camera? Oh, I'm getting distracted. Okay, so I'm looking at the person and trying to guess. It's kind of hard with some people, and all you see is their head, or their head and shoulders. It's really, really difficult to guess their height. And I have an idea of roughly what age the students are, but there is a bit of a range there. And of course, you know, even amongst people who are all the same age, there can be quite a big difference between people's heights. So I'm going to say, I think you are exactly 5 feet tall. So let's do it in inches. I'm going to say 60 inches tall. That is my approximate. Now you type in, and I will recognize your name in the Zoom, so type in how tall you are. 4'9". That's 57 inches, isn't it? 4'9". 4 feet is 4 times 12. That's 48 plus 9 more inches. Yes, 57. Okay, so I'm very proud. I'm pretty close. And because this is actually a rather large number, and I got fairly close to it, percent error is going to be kind of impressive. Teachers are just so good at math, aren't we? Okay, times 100. Don't forget to do the times 100. 60 minus 57 is 3. We don't have a negative number, so we're just writing 3, but we would have just written 3 even if it had been negative. We all know that by now, I hope. And times 100. 3 divided by 57. Certain someone is not going to try to do this in his head. He's already learned his lesson today. And we are getting to the end of the time period for the lesson. So this was a good experiment in the end, although I was kind of slow about setting it up, I admit it. 3 divided by 57 times 100. So I'm getting 0.0526, so 0.053. 0.053 times 100 equals 5.3. Nice. 5.3% error. Now, I can't be the champion of today's lesson because there was at least one student who had a percent error that was 3 point something, guessing one of the colors of one of the colored things. So that student outdid me. But I still feel like I'm pretty good at guessing people's height without having really very much evidence about how tall they might be, because how do you guess that from Zoom, from people in Zoom rectangles? If everyone stood really far from the camera like a teacher, it would be a little bit easier. And I'll leave you with one last thing, which is I'm going to, because I may not have ever said my height in front of any of the students, so I'm going to allow you to try to guess my height, and I will just admit it if anyone gets it right on before I finish this lesson, which is going to be very soon, because it's time to say goodbye. It's time for me to say goodbye. I'm going to say thank you for learning percent error with me. Thank you for interacting, because when students are involved in the lesson, it's just more fun. And I am going to let Mocha say goodbye as well. Come here, come on. Oh, she was really comfortable. I don't know if she's happy with me right now, but she'll be happy in a couple of minutes when I get her upstairs and feed her supper, right? No idea what I'm talking about, right? And I'm looking at no one has guessed my height, except now someone has, yes. So that someone is correct. I am exactly 6 feet tall. And with that, I will say goodbye until next time.